In this screencast, we're going to talk about position, distance traveled, velocity, speed, and we're going to start to talk about the physics of what happens when an object moves with constant velocity. We'll also be introducing some calculus-y terms, derivative and integral, but in a non-calculus-y way. So what I'd like to do at first is to do a little demo with a sonic motion detector. This is a sonic motion detector, and it emits ultrasound and times how long it takes for that ultrasound to bounce back off of something in its path. And so it can know how far away the thing that's blocking it is. And so if I go like this and turn it on, it can report my position as a function of time, and it can record some other features too. So I'll do a motion where I step away from it and then step back towards it, and we'll see what it records. Here's what the program Logger Pro reported about that motion that I did, where I stepped away from the motion detector and then back towards it. Here's my position as a function of time. Time is on the horizontal axis. So it shows my position increasing. I guess it takes the motion detector as the origin, and positive position is in front of the motion detector. So I move to a more positive position and then a less positive position. That makes sense. Let's look now at the velocity graph. It's a little bit wiggly, but during the time when I'm stepping away from the motion detector, the velocity is always positive. It's not always constant velocity because I wasn't always moving at the same rate away from the motion detector, but when I'm stepping away from the motion detector, I had positive velocity. And then when I moved back towards the motion detector, I had negative velocity. Not constant negative velocity because I wasn't always moving at the same rate, but the velocity was always negative when I was moving back towards the motion detector. Let's take a look at the speed graph, and I'll leave the distance traveled graph for a little bit later. The speed graph looks like it is always positive. But if you look at this moment where my velocity is 0, that's the moment where I'm momentarily stopped as I switch from moving away from the motion detector to moving back towards it. At that moment, the speed is also 0. And if you look at this closely, if you look at the relationship between the velocity and the speed graph, you can see that at every instant the speed has a velocity, or the speed has a value that is the absolute value of velocity. So that is what speed is. Speed, as a function of time, is the absolute value of the velocity as a function of time. So let's see. Here's an example type of problem that we can do with that idea. If this is a given velocity graph where sometimes the velocity is negative and sometimes the velocity is positive, I guess in this case that would be sometimes moving towards a motion detector and sometimes moving away from a motion detector. Can we construct the graph of speed as a function of time? Why, sure. You can just take all the moments where the velocity is negative and show a speed that is equivalent and positive during those times. Great. What is negative velocity? Well, in this case, it means moving towards the motion detector. However, it's not always true that negative velocity means moving towards the origin. This motion detector can only show positive position. We will later find that when an object is in negative position, having negative velocity doesn't mean moving towards the origin, it means moving away from the origin. But we'll talk more about that later. Let's talk now about what distance traveled is. So even as my position can increase and decrease, but the distance that I travel only increases. It is a monotonically increasing function of time, monotonically meaning that it is only ever increasing. Distance traveled, let's see, you can see that it has the same shape as position up to the moment when I switch direction, and then it just continues to increase. Distance traveled is sometimes known as shoe leather distance, like how far has the leather on my shoes traveled. It only accumulates more and more distance. So technically distance traveled is the integral of speed, for those of you who have had calculus. it is fine for our purposes now to just say that distance traveled is like the shoe leather distance, and it is not the same as the position as a function of time. Now, I'd like to show you some different demonstrations involving some buggies that move at constant velocity. This is a buggy or a truck or a cart that moves at roughly constant velocity. See, when I turn it on. So let's see what happens when I measure its motion with the motion detector. Here's what Logger Pro had to say about that motion. Here's the graph of position as a function of time, and here's the graph of velocity as a function of time. And so it took until this time for the cart to start going. I started the recording before I actually started the cart moving. So this period represents the cart that's more or less still. What I can do here is take this and auto scale it from 0. It shows you that that the cart had a position of about 20 centimeters up until a time of about 1.7 seconds. And then what happened? When the cart was moving, this seems to be a reasonably linearly increasing position as a function of time. And look at the velocity. It is, it's got some bumps, but it is roughly constant. It was roughly 0. And then it went to roughly, I guess I'm looking down there in the lower left-hand corner where it's showing me the value. It's roughly 18 centimeters a second, 0.179 meters per second. Is about 18 centimeters for each second. And so yes, this is a roughly constant velocity, which gave a roughly linearly increasing position. Now, let me show you a different buggy that goes faster. By the way, the first one was blue, but this trace showed up as red. I'm about to show you a fast red buggy, but Logger Pro is going to show that trace as being blue. So it'll be confusing, and you'll be able to handle it. Here's the red buggy. This is a faster buggy. Let's see what the motion detector says about its motion. So here's Logger Pro displaying the position and velocity of both the fast cart, that's the blue one, and the slow cart, that's the red one. That is to say, the graph of the fast one is blue, and the graph of the slow one is red. So maybe you predicted this, that there is a steeper line indicating the position of the function of time, a line with a higher slope for the fast cart than for the slow cart. And if you look at the velocity as a function of time, these bumps are not all that significant. They come from maybe bumps in the tread of the tire or small imperfections with the measuring. But you can see a roughly constant velocity for the fast cart that is higher than the roughly constant velocity for the slow cart. And so now, I guess I'd like to show you some various things that Logger Pro can measure. Well, one thing that I can measure with Logger Pro, if I select a particular region and a graph, is if I go to this statistics option, I can display some statistics about each of the graphs. And so here, Logger Pro is telling me that the average value for this fast velocity is, let's see, the mean is 0.2266. So that's 0.2266 meters per second, so about 23 centimeters a second, compared to only about 17 centimeters a second for the slower cart. Here's another thing that Logger Pro can measure for me, is if I highlight this relevant region, and I guess right now, let's have me only I'll hide the fast data set and look at only the slow data set. I'm going to have Logger Pro fit a line to this region that I've highlighted with the linear fit tool for run 1. Okay, and let's see what it says. It says the slope is about 0.1733. Well, what are the units of this slope? Well, a slope is always a rise over a run. The rise has units of meters, and the run has units of seconds. So the rise over the run has units of meters over seconds, meters per second. And this particular slope has a value of about 0.17 meters per second. Well, that rings a bell. Let's see this again. If I go to the statistics there, the value of this average velocity was about 0.17 centimeters a second. So the velocity that this cart had is the same as the slope of its position function. So that is definitely a result that we will care about. The slope of this constant velocity position function is velocity. To use a calculus term, the derivative of the position is the velocity. Okay, very good. So that's one thing that LoggerPro can measure for me, is the slope or the derivative of this line. Let me show you another thing that LoggerPro can measure for me. It's also a relatively calculus-y thing. On this region, when the cart is moving, it can do this. It can show me what's called the integral of the velocity. And the integral, for now, is like the area between the function and the horizontal axis. And let's think about what units should that integral have. What units should this? It's not quite a rectangle, but if it were a perfectly constant velocity, it would be a rectangle. Well, the base would have units of seconds, and the height of the rectangle would have units of meters per second, right? Because that's the unit of the vertical axis here. So let's see, a second times a meter per second is units of meters. And so this integral has a value of 0.33 meters, about 33 centimeters. Does that relate to anything physical? Well, let me show you this. As I hover my cursor here, I see that the position of the cart at the start of this time interval is about 29.5 centimeters. And at the end of the time interval, it's about 62.5, or about 63 centimeters. So yes, indeed, if you do the math, you see that the change in position, the amount that the cart's position has changed, is the same as the value of this integral, this area between the velocity and the horizontal axis. And that's something that we're going to care about. All right, one more demo, and I'm going to show you what happens when you set a buggy going towards the motion detector. See if you can guess what that graph will look like. Now I'm going to send the buggy towards the motion detector. With this graph, there was no delay between the time I started recording and the time I let the buggy go. And as you can see, the position as a function of time is linearly, steadily decreasing, and there is a roughly constant negative velocity. Again, these bumps are probably due to the imperfections of the tires on the buggy. But if you can believe me that this looks like a pretty linearly decreasing position, then you can believe me that this is a roughly constant negative velocity. So let's see if we can use LoggerPro to report the derivative of this position as a function of time. It looks like it has a derivative of about negative 0.15 meters per second. Negative 0.15 meters per second. I guess the negative in this case refers to having a negative velocity, a velocity that is towards the motion detector. And again, the units are meters per second. Let's see if we can find the average value of the velocity. Turns out to be negative 0.1533 meters per second. So once again, the derivative of the position is the value of the velocity. Let's see what happens when I find the integral of the velocity over, say, this region. I'll use the integral tool there. And so now it the shaded region is between this negative velocity and, again, the horizontal axis. And its value comes in at minus 0.18, let's see, a second times a meter per second. That comes from having a base of this rectangle with units of seconds and a height of this rectangle, if you like, with units of meters per second. So this is a number of meters. This is about minus 0.18 meters, minus 18 centimeters. And what is minus 0.18 centimeters about the motion of the cart during this interval? Well, let's see. I can hover my mouse here, and Logger Pro is telling me that we start at about a position of about 84 centimeters from the motion detector and end at a position of about 66 centimeters. So yes, indeed, we have decreased our position by about 18 centimeters. So this negative integral, this negative change in position, this negative displacement refers to a position that decreases instead of increases. So let's summarize and codify what we've learned from this card. First, the derivative of position is velocity. In this case, the slope of the position as a function of time graph is the value of the velocity. So here's a question that you could be asked. Given this graph of position as a function of time, what is the velocity of this cart? You might pause the video and see if you can do it either on paper or in your head. Well, let's see. Let's see if we can figure out the value of the derivative of this linear graph. It's the slope, it's the rise over the run, and it works out to minus 2 meters per second. That is the value of the velocity. I guess the speed would be positive 2 meters per second. Okay, another result of this lab is that over an interval, the integral of velocity, which is the same as the area between the velocity graph and the horizontal axis, and the integral can be negative, the value of the integral of velocity is the same as the change in position. And we have a special word for the change in position. It's displacement. We abbreviate it delta x. It means the final position minus the initial position. So here's an example of a question that you could be asked. If this is the velocity of an object as a function of time, what is the displacement of the object between 1 and 5 seconds? You might pause the video to see if you can do that. All right, well, the integral of velocity is the displacement, and the integral of velocity is that sort of area below the horizontal axis there. Because this is constant velocity, this is the area of a rectangle, and it's something you can solve with your geometry skills. There's a base of 4 seconds and a height, if you like, of negative 3 meters per second of this rectangle for a displacement of minus 12 meters. What does it mean that the displacement is negative? I guess if the displacement is the final position minus the initial position, a negative displacement means that the final position is more negative than the initial position. The initial position is a larger value than the final position. If you like, this involves moving towards a more negative position, which is the same as saying the velocity had a negative value. In other words, negative velocity is moving towards more negative position. That's not always towards the origin, as we'll see later. And what is negative displacement? It's ending at a more negative position than the start. All right, so we have encountered our first model in our physics class. A model of physical law is something that you hold in your head, and there are different ways that you can express a model of a physical law. Our graphical way of expressing constant velocity involves a linear position as a function of time and a flat or constant velocity as a function of time. We also have a mathematical expression of this model, and this is not quite it yet, or I guess it could be, but the way that I'll end up expressing the mathematical model of constant velocity is like this. Because the velocity is the slope of the position graph, the velocity is equal to delta x over delta t, and so delta x is equal to v times delta t. The displacement over a given time interval is equal to the velocity times the amount of elapsed time. That's our mathematical expression of constant velocity model. Let me read you this line. The units of velocity are meters per second. So when I use those square brackets, I'm meaning the units of meters per second. What does per mean? It means for each. For every second, there are this many meters of displacement. 2 meters per second means that for each second, there are 2 meters of displacement. A ratio is involved.